Anyway, let's start at the beginning. So ever since I was a child, I've been pretty interested in business and in businesses. And over the years, as my friends will tell you, I've started more than my fair share of harebrained schemes, much to the amusement of them. You can see some of the businesses that I tried to start over the years on the slide. But the really wonderful thing about trying things out in business is even if the idea fails, you still learn a lot. And you can take all those learnings forward into your next idea, which with a bit of luck might be a bit more successful. And that theory of really learning from your mistakes works really well when you're thinking about innovation, and particularly in a corporate environment. So as I said, in 2017, much like the marvelous James Joyce does here, I was leading the innovation activities for NatWest Markets, and I found it a really fascinating journey. I am a technologist at heart, but I wasn't really aware of these new emerging technologies, things like blockchain with tokenization, cloud computing, and of course, machine learning, which we'll talk about today. And I was particularly fascinated by machine learning, I've got to say. We made it a real priority for the NatWest Markets business back in 2016, because we had identified its potential, really, not just to predict prices for financial instruments, which is what most people think about, but to support the businesses really front to back. So machine learning, just to hopefully level everyone on the same page, is part of a field of science called AI, or artificial intelligence. And obviously everybody's talking about it, particularly at the moment, with things like DALL-E and Open API and ChatGPT. But what does it mean? What is machine learning? And honestly, in some of the previous roles I did, I really thought that people were interpreting it as a way to predict the future. And it most certainly is not. A definition that I like is that machine learning is the process to enable a computer to become better at a specific task by considering how that task was completed historically. But in most business applications that I've seen, we all seem to end up using machine learning to try to predict the outcome based on some historical data. And in that sense, it's really a highly sophisticated form of pattern recognition. So I thought I'd start the talk today by sharing with you one of the real formative events for me with my machine learning. And that was with a presentation from a colleague of mine called Will McGee. He was the head quant at NatWest Markets. And before I was attending his presentation, I was expecting it to be filled, like James intimated earlier on, with complicated maths. And I thought it actually might be quite boring. So while I know a bit of maths, I'm no statistician. Anyway, surprisingly, Will started his presentation by talking about a game of noughts and crosses. Some of you might be aware of this as tic-tac-toe, by the way. So if you bear with me, here's a quick rule refresh. The game's played in pairs, and you start by drawing a grid with 9 boxes. The players take it in turns to put a symbol onto the grid. One player uses a nought, and the other player uses a cross. And the winner is the first player to create a line of 3 noughts and crosses in any direction, horizontally, vertically, diagonally. And it is quite good fun. Now, this is Donald Mitchie. He was a British researcher in artificial intelligence at Bletchley Park during World War II. So you've probably heard of Bletchley Park because of Alan Turing, the famous English mathematician who helped to crack the codes in the Enigma machines, during the war. So Donald worked with Alan. And we think that sometime in the 1960s, Donald Mitchie had a bet with a colleague in the computer science department that it wouldn't be possible to create a machine that could learn to play a game and then beat its human opponent. Now, Mitchie didn't have a computer available. It was the 1960s. So he decided to create one using matchboxes. He called it Menace, which stands for the Matchbox Educable Noughts and Crosses Engine. This is what it looked like. The machine consisted of 304 matchboxes, which Mitchie had glued together in a way that was a bit similar to a chest of drawers. For Menace to work, Mitchie gave each box a number. and the numbers link to a drawing of a partially complete noughts and crosses game. So here's a game grid number 199 corresponding to matchbox 199. So Donald created lots of drawings to represent every possible grid that a game could go through as it progressed. There were 304, hence the 304 matchboxes. Next, Mitchie collected some coloured beads. There were 9 different colours to represent the 9 different squares in the grid. Many had hundreds of beads, which he put into the matchboxes so the machine was ready to play. And actually, we're ready to play now. So the human player was always crosses, and Menace would always play noughts. As the human player made a move, an assistant would look through all the drawings that Donald had made to find the one that matched the current grid layout. The assistant then used the number on the grid to locate the corresponding matchbox. Here's number 2. The assistant then shook the beads around in the matchbox and opened it up. And thanks to a little V, cardboard V you can see here at the front of the matchbox, it was easy to see which bead had been selected by the matchbox. In this example, it's the black one. This obviously showed Menace the move that Menace wanted to play, and the assistant could then mark the corresponding nought on the grid. So the game continued, with each matchbox being replaced after a move was played. But for played moves, the assistant left the matchbox drawer ever so slightly open. At the end of the game, if the human had won, Menace was punished by removing the selected bead from all the open boxes. But if Menace had won, the assistant would reward it by adding 3 more beads of the same colour to the matchbox. And as the game was repeated over and over and over again, it became more and more likely to select beads which caused Menace to win the game, and so Menace effectively learns and improves at the game. It really was very clever. Mitchie's matchbox system proved that the computer could learn from both failure and success to become better at a task. And this is a topic called reinforcement learning, which has become a key principle for machine learning. And Menace actually is now viewed as one of the key milestones in machine learning. Personally, I love it because I think it's a real fascinating example and very easy to follow. So back to the present day, it's 2019, and my friend Liz has decided to leave her important job in insurance. We meet a few times for lunch, and as we both love animals, we found ourselves starting to talk about how we could potentially disrupt the pet insurance market in the UK. So by the time the pandemic was in full flow in 2020, we had really solid foundations for an idea, and we were pretty excited by the potential. But first, for those of you who don't know anything about insurance, here's a 10-second primer. Insurance exists as a way to manage risk. So you buy insurance to protect yourself against risk which would cause an unexpected financial loss. You buy a policy, you pay a premium, and that's normally once a month or once a year. And if the risky thing happens, you make a claim and the insurance company covers the loss. If the risky thing doesn't happen, the insurance company keeps the premium. So let's hope this poor lady had some insurance. Effectively, the insurance premiums for a lot of people are pooled together and used to cover the financial losses of the unlucky few, with the insurer being able to cover its costs and make a small profit. For pet insurance, the risky thing is your beloved pet getting sick unexpectedly and landing you with a large bill. And if you're not pet owners, you're not from London, just to give you an example, if your dog was involved in a road traffic accident in London and it needed to go to hospital, it would probably cost you around £1,000 a day just for the animal to be in the hospital before any treatments are given. So a serious accident could easily set you back between £5,000 and £10,000. So here's our business, Pet Proactive. And we think we've got a unique business model. For all other pet insurance providers, the pet owner responds to an expensive advert, perhaps on television, to buy the insurance, and then they can take their pet, if it gets sick, to any vet in the UK to have it treated. It's very difficult with this model for the insurer to know how much it will cost. And it's very difficult for the customer to know what's covered, because the insurer only decides what's covered and works out what they might need to exclude at the point the customer needs to make a claim when the animal's sick. So with our pet insurance, we advertise in your local independent vet, and our insurance products are priced to the vet's treatment prices and behaviours. We think you get a better product at a lower price in return for your loyalty to the practice. And it's working out the price where we use machine learning. Before we get to that, I just wanted to give you a quick overview of our business model. So in step one, we form a contractual partnership with the independent vet. We hoover up all their medical records and clean them in a private data analytics engine that we've built in the cloud. And then we use machine learning to spot patterns in the treatment costs. And we launch a co-branded product to the customers of the practice. Because we've got all the medical records, the customer can get a price instantly. We just have to make sure we manage this in a GDPR compliant way. And because we've got all the medical records, we can confirm all the existing health conditions we need to exclude at the start of the policy, not when the customer might need to make a claim. If the pet gets sick, we pay the vet, so there's nothing for the customer to worry about. And at the end of the year, we share any profit that we've made with the vet to thank them and to encourage them to keep their costs low. So let's go back to the pricing. The way all insurers price things involves looking at the claims. This is their data. Pet insurers insure lots of animals, and then they wait for some claims to come in from the sick ones. And when the claims come in, they note the characteristics of the animals, which cause them to pay out. So the only point of data the insurer receives, which is useful, is the claim. So let's have a look at the UK market leader for pet insurance. Imagine we've got 100 dogs. In the UK, about a third of people on average insure their dog. So a third of 100, well, that's 33 dogs. The market leading pet insurer in the UK has about a 20% share. We're down to 6 dogs. The likelihood of a dog making a claim, so the insurer gets some information, varies, but it is about 20%. We're down to 1 dog. So the market leading pet insurer in the UK has information on 1 dog in every 100 that exists. And even though they're the market leader and they have lots of dogs, the dogs are all over the country. So the density of dogs in any particular area and the quality of data they get is quite low. Because we partner with the vets, we have information on 100 dogs in the area of the practice. And that includes the ones that aren't insured. Unfortunately, and I'm sure this will come as no surprise to many of you when you look at data that you have to deal with in your own job, the data that the vets use is in a real mess. Vet practices use software to manage their businesses. They change software packages. They have different staff with different levels of IT skill that choose to use the software in different ways. And vets at the same practice come from different countries and cultures. They speak different languages. They prefer using different drugs. And they use different shorthand when they make notes about treating the animals. Pet owners themselves have strange behaviors. They might visit different branches of the practice. They might lie. The pet might arrive with another family member one day, and the pet owners, they might get divorced. All of these things and many more fragment the data, and they make it difficult to use. So our first job, before we could even think about how we price insurance, was to build a way to clean up the data. And I think we've done it. We have lent on some of the solid principles from financial services, but in this slide at the bottom, there's a sort of indication of of the vet's view of the world in blue and of our cleaned world of the view of the world in green. So for example, if we went into this particular vet practice, they'd say, you know what, I've got 52,845 customers. But after we've run our analytics, we've joined them all up, cleaned up all the fragmentation, we tell them, no, you haven't. You've got 39,331. And that cleansing process occurs across all of the facets of data at the vet. And then we can do really interesting things, which we're hinting at in the bottom right. And this chart, while it's really tiny, what it's showing is how the vet, the particular practice, has changed the parasite treatment costs for dogs over a 5-year period. Okay, great. So now I'm going to show you a spreadsheet, which hopefully isn't too boring, but this is what the data looks like once we've cleaned it up. So you can see there's a unique identifier for each dog, and there are different identifiers here, which are the codes for a breed: a French Bulldog, a Cockapoo, a West Highland White Terrier. The age of the animal is here, and this is all real data from the vet. And we can see that the cost here is the cost to treat that animal in that calendar year. Now, there's lots of secret information at the top here. And unfortunately, I have to keep it secret because this is a really commercially sensitive information. But it gives you an idea that we have other information as well as the age and the breed for the cost here. So imagine our goal is to predict how much an animal will cost to treat based on the characteristics that are available for us, right? How do we turn this data into a swanky price prediction machine with machine learning? And one of the first things we have to do is identify a smaller set of pet characteristics. So I'm going to pick one of these characteristics, age, and I'm going to just plot cost against age. What happens to treatment cost with age? Put another way, will older animals be more expensive to insure? And how do we find out? So there really are lots of ways that we can get comfortable with the data. But one of the first things I like to do is to plot a scatter chart. The scatter chart visualizes the data. It's something that's available in Excel. And what I've done here is I've put the thing that we want to predict on the vertical axis, that's the cost. And I've put the thing that we think will help us predict it, that's the age, on the horizontal axis. Now, purists would call this the dependent variable and the horizontal axis the independent variable. I've fallen into the habits of using machine learning-like language. So I refer to age as a feature that helps us to predict cost. So I've produced this chart in my special software that's a little bit more powerful than Excel. You could use Excel to do this sort of stuff. I've tidied it up a little bit in this example. And to begin with, it's quite difficult to interpret, I think. At first glance, it doesn't look too helpful. You're looking at 50,000 dots for about 50,000 dogs, but very highly correlated data where the feature really drives the prediction is actually much easier to see. So here's another example. Basically shows the number of minutes that you spend on a treadmill, with the predictor being the number of calories that you burn. Just from looking at the graph, you can see the pattern of the data there, that the longer you spend on the treadmill, no surprise, you burn more calories. We can easily draw a line of best fit here for the data so we can see it. And this line is really helpful because it turns the scatter graph into a prediction machine. I can now go and find any point on this feature axis here, the duration. I can trace a line up and draw across to the calories, and then I get an idea of how many calories might be burnt at that time point, at that duration, even if that data wasn't originally available. So if we continued this line, we might be able to see how many calories would be burned in 60 minutes, for example, or I could be more precise. I could be interested in 15 minutes and 17 seconds. So with our scatter graph, it's not very easy to immediately see a line of best fit. But thankfully, two scientists in around 1805 worked out some maths for this as they were trying to work out how planets moved around. The maths is called least squares, Again, it's available in Excel and other software. You can just punch some stuff in and you get a line of best fit. When we add the line of best fit to our scatter graph, we've created our prediction engine. Probably a fancier name for that is a linear regression. It doesn't look particularly powerful when you look at it like this, but if you collapse the scale, the correlation to cost for age is quite strong for dogs. And we can see that the cost significantly increases, £100 going up to over £200 over the 10-year period of the animal aging. So we now have a crude way to predict insurance prices based on a dog's age. And it is really crude because it's a straight line, linear. We could improve it by making it a curve with something that we might call a polynomial regression, or we could use some other method. But in my experience, doing this is enough to identify a good correlation between the thing I want to predict, the cost, and the thing that I think might help me predict it, in this case, the age. At Pet Proactive, we have spent a really long time with this approach to look at different pet characteristics and also derivatives of those characteristics that we could turn into features to show how strongly they correlate with things that we want to predict. So here's an example of some of the other features that we found that correlate really strongly with cost. Quite a lot of these are secret, so that's why you're seeing a question mark appearing in this in this graph, again, because it's our IP. But what we have shown you here is that cost varies quite a lot based on the breed of animal that you have. So one breed here is less than £150 on average a year, and one breed here is maybe £270 a year. But that actually gives us a bit of a problem, actually, because how do we deal with that? If we've got two factors, for example, if we encounter a 3-year-old Labrador Retriever, how would we price that? We couldn't use our linear regression. There are some conventional methods for doing this, things that you might have heard of, like a generalized linear machine used by a lot of insurers. We experimented with these, but this really, because of our ability with the amount of data that we've got from the vets, is a perfect opportunity for us to start leveraging machine learning. So what we do for that is we take our huge data set of pets and we add all the features, things that we wanted, like age and breed and some other things that we've come up with, to create basically a spreadsheet where all the rows are the pets and all the columns are the features. We use some software to divide the pets into two groups. We create a large set of data, which we call the training set, and that's what the machine learning software will use to learn how the features interrelate to predict cost. And we take a smaller set of data away, a smaller number of pets away, to use as a test set. So it's a test set because we actually know the cost of the animals, but if we don't tell the model about it, when the model runs, we can see how accurate it is. What the machine learning algorithm does is it really encapsulates about 300 years of mathematical theory for us. We really don't need to know much maths in order to run this style of prediction. The model basically joins up all the features we want to use, like age and breed, across the thousands of pets in the training set, and it is able to find the pattern. And the results out of the box with these sort of machine learning APIs that are available for all the major languages are pretty compelling, really. One thing I'm just saying, you're probably thinking, why am I looking at a picture of the dog? Those in the UK might recognize this dog because it's recently been classified as the oldest dog in the world. I think it lives in Portugal or Spain. It's 30 years old, this dog, with its friend, the cat there. But we have to be a little bit careful when we use the machine learning engine, because we have to overlay some rules of our own. The machine learning model doesn't really understand real world rules, such as, a human wouldn't pay £500,000 for an insurance policy for their dog, or, there can't be a 50-year-old dog. It doesn't understand those things, and those can somehow create problems. But let's go back to our model. And this is a way we visualize the results of our model effectively. Now, this is quite common in insurance. Again, each row in this spreadsheet represents a dog. What we're doing now is we've got some factors that go into our model here. We've got the predictions here, what our machine learning model is predicting these individual animals will cost. And then we've got some competitor pricing here, which we're doing some analysis on. But at the end here, in this column, this is the results of the model. So after the model's been trained, what we've done in our example is we've asked the model, given these factors that we put into the model, we would like it to predict, first of all, the likelihood of there being a claim. So that is a percentage. And then if there is a claim, the severity of the claim, how much it thinks it will cost. So if I highlight a pet here, we've got what looks like a 2-year-old German Shepherd. And we're saying that we think that there's a 31% of that costing us some money. And if it does cost us some money, the average bill will be £493. Now, the more observant amongst you will notice at the top of this thing here, we've got some summary data. And this was the really staggering thing when we ran this. We just couldn't quite believe how accurate the model was. So what this is telling us here is these are fees. So we train the model with 5 years of data, and then we ask it to predict the last year of pet data, data that it hasn't seen before. And we can see that the characteristics that we've chosen are pretty effective. The actual vet bill was just over 3 million, and the machine learning model predicted within 1.5% on the aggregate. So it gets a bit more complicated as you break down into the individual breeds, but I would hazard a guess this is a very accurate pricing prediction for this this product. So what we tend to do with that when we're talking to vets, it's a bit difficult going through all those numbers. So we produce this sort of chart from our pricing model. And what this shows is the range of prices that our model will come up with for different characteristics as a pet ages. And then the red line shows the competitors' pricing in the area. So it's quite easy then for the vet to visualize that we're going to beat all the competitors quite a lot of the time, basically. Great. So once we've produced the models, one of the things we do is we upload them into the cloud. So all of our software sits on cloud computing systems, and we use Google. So here you can see all of the models in the cloud, a little bit like maybe how some of you would access a web page. We just make a request from a piece of software that's a bit like asking a web page. We send all the details of the dog to the pricing model, and it gives us a price. So we might say, hey, I've got a 5-year-old male neutered Rottweiler. What's it going to cost me? We get a price back, and we can present that to the customer. So I thought I'd end the presentation by just doing a little demo on how our software works and how all of that comes together to make a customer-facing product. But one of the things that's sometimes helpful to do is to draw a comparison. You know, how do our competitors do this? So one of the big insurers in the UK is Animal Friends. If I wanted to insure my animal with Animal Friends, this is the process that I have to go through. Here I would have to select my animal. Some questions have appeared. I'm not sure why this is important. My dog's name, okay. Do I want to cover for things in the past? Yes, I do. Okay, they can't cover me, I don't. Oh gosh, there's so much information to enter. And that's just for one pet. I'm going to have to run away and find information. So here's our website, the Pet Proactive website. And if I want to get a quote, quite simple, let me just get my mobile phone. This, by the way, is what we call a pre-production environment. So it's a little bit slower than our production environment because we're doing a test today with you guys. So if I'm a Pet Proactive customer, I scan a QR code in the vet, or I visit a website, a web address on one of the posters, and I basically land on this page where all I have to do is enter my mobile number to prove my identity. And then after a few seconds, I'll switch my sound on so you can hear it maybe. because it's a little bit, oh, here we go, there's the thing, great. Because it's in a development environment, sometimes these things have to spin up. I'm going to enter my code that I've been texted. Here we go. And then the vet practice sends data on all the animals across, and I see all of my prices immediately. You can see the animals being priced here as we send requests off to the pricing engine. And if I click into one of them to ensure, then I get prices for our different products instantly. So it's a much cleaner process, and all of my animals have been priced. That's all thanks to the lovely machine learning. So this really completes the demo. Hopefully it's not been too boring or in-depth. I hope you've found it useful. If there's any key takeaway today, I would argue that the machine learning now is actually pretty much a simple and fairly commoditized process for your technology teams. There's a lot of out-of-box solutions and APIs which have great performance and results. The challenge here is in the data, and that is the competitive differentiator. So it's access to the data and having somebody or some people that spend enough time with it to really understand it, so they can organize it in a way that drives the outcomes you want from the machine learning science. Great, that completes my presentation. Thank you very much. I'll hand back to James or Carl. Thanks very much for inviting me, by the way.